Hello, my name is Rachel Lively, and I am a junior studying chemical engineering. This is my second year working with Professor Mike McGurk on the Hydrogen Storage and Delivery in Porous Frameworks project. Our overall focus is to develop porous materials capable of efficiently storing and delivering hydrogen at relevant pressures and ambient temperature for use as an alternative fuel source. As you may know, the fossil fuels we rely heavily on are contributing to the increasing greenhouse gas issue. For this reason, scientists are currently searching for a new eco-friendly fuel source. We are investing the time and energy into exploring hydrogen because it has great potential, including the highest energy per mass of any fuel, power generation through a reaction rather than combustion, and eco-friendly byproduct of water. However, hydrogen does have drawbacks. It is very low density and requires significant energy and therefore money to cool and pressurize for delivery in large amounts. For this reason, metal organic frameworks, known as MOFs, have been explored as a material-based storage for hydrogen. A MOF is composed of a metal node and an organic linker unit, which are repeated to create a 3D porous framework. MOFs act as a sponge to soak up and store the hydrogen on their internal surface area. This method of gas storage and delivery allows for better performance and lower costs when compared to physical-based methods such as tanks and pipelines. Zeolitic imidazolate frameworks, known as ZIFs, are a subfamily of MOFs that display exceptional stability. One specific ZIF, known as ZIF7, is formed by connecting zinc metal clusters through benzimidazole linkers. This ZIF has been explored by our group in the past and has shown great efficiency in storing and delivering hydrogen, as well as other small molecules such as carbon dioxide and ethylene. Since separation of gas mixtures is of great importance in the chemical industry, the scope of my research was broadened to include these other small molecules in an attempt to best understand the fundamental interactions and adsorption properties of this framework. I began by setting up density functional theory calculations with chemically logical starting points to explore the attractive interactions between small molecules in the surface of the framework to ultimately find the lowest energy state. By analyzing electrostatic potential maps of the small molecules, which illustrate the regions of high electrostatic potential in blue and low electrostatic potential in red, we were able to predict and explain the very complex interactions. However, since I don't have time to go into detail about every small molecule that was tested, I will spend the rest of my presentation illustrating the process with hydrogen and ethylene. As you can observe from the ESP map, hydrogen has a positive potential region on either end. Ethylene, on the other hand, has a negative region in the middle where the double bond is located and a positive potential region on the outside from the 4 hydrogens. Since ZIF7 is so complex, we have tried to minimize the computational cost while still modeling the system to understand the real-world behavior. For the first model, we tested benzimidazole, which is the linker in the real cluster. In the hydrogen calculations, we observed the positive electrostatic potential ends of hydrogen orienting to interact with the negative electrostatic potential on the nitrogen. In the ethylene calculations, the double bond with negative electrostatic potential is orienting to interact with the positive electrostatic potential in the benzimidazole ring. This is important for our calculations because the region of positive electrostatic potential isn't present in the larger cluster due to benzimidazole deprotonation and metal coordination. Since the ligand isn't accurately represented because the NH groups don't exist in the real cluster, we had to increase complexity to better model the system. In this cluster, the central area is representative of the real cluster, but the ligands remain simplified. In both hydrogen and ethylene calculations, we see them continue to orient in the same way as we saw with the benzimidazole calculations, interacting with the CH group of the benzene ring rather than the pi cloud. Highlighted on the right is the CH bond that we see ethylene interacting with. As you can see in the ESP map of the cluster, there are regions of high and low electron density on the outside of the cluster. These regions are more extreme than the real cluster and again pose problems for our calculations. Therefore, we again had to increase the complexity to try to minimize the effect of the polar bonds. In this model, despite the newly added ligand complexity, we see hydrogen continue to interact with the CH groups on the benzene ring. Ethylene, on the other hand, moves towards the Lewis basic nitrogen on the right side of the cluster. As you can see in this ESP map, even though we eliminated the large regions of electron density, we still have sections with extreme electron density. This explains why ethylene moves from the benzimidazole ring to the nitrogen in the negative electrostatic potential region on the right side. Since our attempts to minimize complexity and save time in computation weren't successful, we moved back to our starting structure, ZIF7. At this point, I aimed to build an exact model of the framework for calculations. The photo on the left is this exact model, which illustrates just one unit that is repeated in the framework. After trying to run calculations with this model, we determined it was too computationally time-intensive. For this reason, I took a step back to form a slightly less complex model, shown on the right, which has the same inside structure and hyperlinkers on the outside. Going forward, I'm continuing to run calculations with this model to explore its interactions with various small molecules. I appreciate your interest in my research, which I have been working hard on all year and am excited to finally get to share. Thank you for taking the time to listen to my presentation.